Hello class, welcome to Module 3. In this module we're going to talk about another aspect of inferential statistics called hypothesis testing. So to understand what hypothesis testing is, I need to give you a number of definitions. Once I give you the definitions, I'll show you how to apply those definitions to solve meaningful inferential statistic problems. So let's start with the definition for hypothesis. A hypothesis is a claim or statement about a property of a population. Okay? A hypothesis test is a procedure for testing that claim about a property of a population from a sample. The null hypothesis, usually denoted by H sub 0, that's a typo, that should be subscript 0, is a hypothesis that results from a sample based on chance. So the null hypothesis is a result that comes from a sample that says that the property that you're trying to characterize the population with is a chance occurrence. Okay, so chance. The alternate hypothesis comes from the sample, and it says that the property of the population does not occur by chance, that something contributed to that property of the population. It is not a chance occurrence. And it's usually symbolized by H sub A or H sub 1. And again, I didn't show the subscripts in the notes. The symbolic form of alternate hypotheses must use either a less than, greater than, or not equal sign. So one of those three symbols. And I'll show you the structure of that. Let's talk about critical values. A critical value is a point on the standard normal distribution beyond which we reject the null hypothesis if the test statistic to be defined or determined falls in that region. The critical value can be positive or negative. So let me show you that. Alright, so what we're going to be doing is this. You have a standard normal distribution curve, okay? And you find a critical value. Okay? So here's, which I used a subscript CRIT for critical value. Now, if it happens that you calculate a test statistic, and I'll show you how, and the number for that test statistic is bigger than this critical value, okay, then there was no chance occurrence. Okay, you reject the null hypothesis. Okay, so if your test statistic, which you will calculate, falls in these shaded regions, these are reject regions. Okay, you reject the null hypothesis, and I'll explain more later. But if your test statistic that you will calculate is between these two values, then you do not reject H naught. Okay, your null hypothesis. Do not reject. So the conclusion is that the inference you're making about the population is due to chance. All right, so more on that later. This is a little bit on the abstract side. I'll make it more meaningful very shortly. So critical values are found in the z, t, or chi-squared tables depending on which type of test you are conducting. A critical value is a number that indicates how many standard deviations away from the mean it is. It can be positive or negative, and it's based on what the significance level is. So critical values are determined from alpha. So remember in Module 2, I would give you a confidence level, and then you convert that confidence percentage, okay, into a decimal, and then you would get alpha from that decimal. 1 minus, for instance, 1 minus 0.9 is 0.1, gives you an alpha. And then you would have that, okay, to get 0.05, and on occasion you would take that 0.05 and subtract it from 1. Okay, so if you took this 0.95, okay, as a probability, and you went into your standard normal table, so let me open up my standard normal tables. Let's see here. I'll go ahead and open up all of them. That's my chi-squared table. I want the standard normal table, and I'll open up my student t table since we'll be working with that as well. Okay, and then my standard normal table. Okay, so if we take 0.95 as the probability, what is the associated z value, z-score? okay, the z-statistic. So we hunt for 0.95 right here, and we discover that it's 1.645 is the z-score, okay? But if we hunt for, 0.05, okay, 0.05, that would be alpha over 2. Okay, that would also indicate a z-score of 1.645 as well. So let's see, we need to find 0.05 probability. Where is that? Okay, so that'll be here. Okay, so 0.05, just to reiterate, 0.05 is where? 44849, right here. So again, that's negative 1.645. So in this table, the author of the table made an omission. If you want the probability for 0.05, that's negative 1.645. So just to clarify an omission in this particular table, you should put a plus or minus sign here. The minus sign being associated with this particular alpha over 2, and then the plus 1.645 is associated with 1 minus alpha over 2. And if you want to plug in numbers, this would be minus 1.645, and then this would be 1.645. Okay, so that's how the critical values are analyzed. Okay, so let's talk about test statistics. Okay, these are the things that you need to calculate. Okay, the test statistic is the value used in making a decision about the null hypothesis, and it's found by converting the statistic. Okay, and the statistics we will work with will be the same as those from module 2. They'll be proportion, mean, standard deviation, or variance. And so the test statistic is a value used in making a decision about the null hypothesis, and is found by converting the statistic obtained from a sample to a score with the assumption that the null hypothesis is true. Okay, so that's the test statistic. Now here's the key point right here. If the test statistic has a higher value than a positive critical value or a lower value than a negative critical value, then the null hypothesis is rejected. So going back here, okay, if your test statistic, and I'll show you how to find those, falls here, if it's less than the negative value or if it's greater than the positive value for the critical value, then again you reject the null hypothesis. So how do you calculate test statistics? Okay, so here's the table that shows you how. All right, if you're analyzing a hypothesis about a proportion, okay, and it turns out that the sample size times the probability, check that, the sample size times the proportion, okay, proportion, right, is bigger than 5, and the sample size times 1 minus the proportion is bigger than 5. Remember, Q is 1 minus the proportion. Then the sampling distribution is normal, and you use this formula for the test statistic. Note that in the denominator, that the term under the radical sign, that's P and Q. That's not P hat or Q hat as we've done before, but that's P and Q, so that's the population proportion. Okay, so if we do not know the standard deviation of the population, and let's see, sigma not know, and the population is normally distributed, if we know those, or if we don't know the standard deviation of the population and we know our sample size is bigger than 30, then we have to use the t-statistic, okay, which formula is here. And that we use this if we're analyzing hypotheses about a mean. Okay, another way of analyzing hypotheses about a mean is if we know the standard deviation of the population and the population is normally distributed, or we know the standard deviation of the population and the sample size is bigger than 30. Then we calculate a z-statistic, okay, and the z-statistic is formulated this way. All right, and again, I will show you examples of all three, actually all four. Let's talk about the hypothesis analysis for standard deviation or variance. Okay, in this case, we use a chi-squared statistic. Okay, and to use a chi-squared statistic for hypothesis analysis, you have to be given a statement that the population is normally distributed. And the test statistic for hypothesis testing of standard deviation is this chi-squared statistic. And you will compare that against the critical values which you get from the chi-squared table or from Excel. All right, so let's look at this question. All right. So the claim is that the proportion of drowning deaths of children attributable to beaches is more than 25%. And the sample statistics include a sample size of 696 drowning deaths of children, with 30% of them attributable to beaches. So we want to find the test statistic. Okay, so for this particular problem, we have what? Let's see. This is a proportion, right? Whenever you see percentages, we're dealing with population proportions. So we go to this test statistic table, okay, and we look for the test statistic for a population proportion. Now, in order to use this test statistic, we have to verify these quantities. N times P must be greater than 5, and N times Q must be greater than 5. Well, what is N? N is 696. What is P? P is 25%, right? P is the proportion given. Okay, not the sample proportion. The sample proportion would be P hat. Okay, P hat is 30% coming from your sample. So P is 25. So a fourth of what, 696? That's what, greater than 150, right? You can roughly estimate it. So that's much greater than 5. Likewise, Q is 75, right? 0.75. Q is 0.75. So 3/4 of 696 is much greater than 5. So I'll go for the computation of the Z statistic. Okay, so the formulation for the Z statistic for this problem will be done as follows. Okay, so we have Z equals to sample proportion minus population proportion divided by the square root of population proportion, 1 minus the population proportion divided by sample size. Okay, and so we can use Excel to calculate this number, the Z statistic. Okay, so to do this in Excel, you click in a cell, type equals, okay, and then in your numerator, your sample proportion was 0.3. And then your population proportion was 0.25. Okay, then you divide that by the square root of P, which is 0.25, Q, which is 1 minus 0.25, and that's 0.75, divided by sample size, which was 696. Okay, close paren. And then your Z statistic turns out to be 3.046 or 3.05. Let's go with 3.046. Okay, so that would be your Z statistic for this problem. All right. And later on, I'll show you how you use this to analyze hypotheses. What's next? All right, so we have this so-called two-tailed test. So a two-tailed test is formulated, a two-tailed hypothesis test is formulated using this symbology. You have the null hypothesis, which is equal to something, and I'll show you examples, and then the alternate hypothesis, which is not equal. So two-tailed tests are always characterized by the alternative hypothesis exhibiting a not equal sign. Okay, if it exhibits a less than or greater than sign, then it's a one-tailed test. So alpha is divided equally between the two tails of the critical region. All right, so you use this alpha to calculate these critical values. Okay, and if your test statistic falls within the green region, then you fail to reject H naught or H sub 0. Okay, you fail to reject your null hypothesis, which means that the phenomena that you're investigating probably occurred by chance. However, if your critical, check that, if your test statistic lies in one of these magenta colored regions, okay, then your alternate hypothesis is credible, okay? It's credible, and the phenomena that you're investigating probably occurred by some event other than chance. All right, so now the trick is to formulate your null and alternate hypotheses, and I'll show you some strategies for dealing with that. So in analyzing hypothesis, one technique is called the critical value method, okay? And that's what I just explained. If the test statistic falls within the critical region, reject H naught, okay? The critical region is the magenta colored region in this graph. If the test statistic does not fall within the critical region, fail to reject H naught, and the non-critical region is green, okay? Okay, so let's do this example. In this example, we're going to formulate a null and alternate hypothesis. The manufacturer of a refrigerator system for beer kegs produces refrigerators that are supposed to maintain a true mean temperature mu of 48 degrees Fahrenheit. Okay? The owner of a brewery does not agree with the refrigerator manufacturer and claims that he can prove that the true mean temperature is incorrect. Okay, so here's how you formulate your null and alternate hypotheses. The manufacturer, okay, is of the refrigerator system. All right, so think of that person, the manufacturer, as the specialist, the expert who provides a service, a good, a conclusion, a finding, or as an authority. Okay, so this guy is recognized as a refrigeration specialist, and this guy goes around and he puts labels on all of his appliances saying that my mean temperature on my refrigerators is 48 degrees, and he sells hundreds of these things. Okay, so it's fairly ubiquitous that that the mean temperature of the refrigerators is 48. Okay, and then along comes this guy, this brewer, working out of his garage, and he says, I don't believe you. Okay, I don't believe it. So you have this one lone guy, saying that's not true. Okay, so think about it this way. If you see a manufacturer, if you go into a store and you see a claim posted on if you see a claim about an appliance and you don't believe it, okay, does your belief reign supreme and everything, and then this dealership has to give you money and rebates and all this other thing? No, that's not going to happen. If you don't believe a claim from a manufacturer, you have to prove your claim, okay? And so you have to prove that mu is not 48. In other words, you have to come up with an alternative explanation than the one that's most commonly applied, okay? So that's basically how you generate your alternate hypotheses. So this is the formulation for this problem, all right? So does that answer the question? Okay. Let me see. I'm checking my notes. Yeah. So we'll go with. So this is the formulation of the null and alternate hypotheses. You have the ubiquitous scenario, and then some guy comes along and challenges the common held belief that mu is 48. Okay, somebody takes exception. The alternate hypothesis is an exception to a standard setup. Okay, so let's do some computations that you'll need to perform for hypothesis testing. Excuse me. In a sample of 100 M&Ms, it is found that 8% are brown. Use a 0.05 significance level to test the claim that of the Mars Candy Company that the percentage of brown M&Ms is equal to 13%. Okay, so first identify the null and alternate hypotheses. All right, so again, the ubiquitous occurrence, the most ubiquitous occurrence, or the ubiquitous occurrence of bags of M&Ms is set by the manufacturer to be 13% brown. Okay, 13% content being brown. All right. Then one day you go to the store and you buy a bag of M&Ms and you discover that 8% are brown. Okay, and so you claim that Mars's claim is false. Okay, and so you have to demonstrate that Mars's claim is false. And so you propose an alternate hypothesis that the proportion of M&Ms in a bag of 100 M&Ms is not 13%. And this is your alternate hypothesis. So you have the ubiquitous situation, and then you have an exception to the ubiquitous situation. Okay, and so this is the formulation. Now you need to compute the test statistic. Okay, so since we're dealing with proportions, okay, and let's see, we can assume that the proportion times the sample size is much bigger than 5. Okay, let's see, can we make that assumption? Okay, well, let's see. We have 100 M&Ms, right? So the sample size is 100. So n is equal to 100. And let's see. So NP is 8. Okay. So no, wait. I'm sorry. NP is 13 because P is the proportion. P is 13%. P hat is 8%. P hat comes from the sample, right? So the sample size is 100. 100 times 0.13 is 13, so that's bigger than 5. And then Q is what, 0.87. And so 0.87 times 100 is bigger than 5 as well. So that meets the criteria for the Z statistic. Okay, so what we need to do then is calculate the Z statistic for this hypothesis test. So we have P hat equals to 0.08. P is equal to 0.13. Okay, Q is equal to 1 minus P, which is equal to 0.87. N is equal to 100. Okay, and what else? We have Z, okay, is equal to P hat minus P divided by the square root of PQ over N. Okay, so that would equal to 0.08 minus 0.13 divided by P, which is 0.13 times 0.87 divided by N, which is 100. Okay, for a sample size. Okay, so we can go into Excel and calculate that Z statistic. So pull up Excel. All right, and so select the cell, equals, okay, numerator is 0.08 minus 0.13. Denominator is square root of 0.13 times 0.87 divided by 100. Okay, and so our Z statistic is negative 1.48675. Okay, that's your test. So what is your critical value? So we need to calculate the critical value. So for this problem, what is alpha? Alpha is, how confident do we need to be? .05. Okay. Now remember I showed you earlier, okay, since whenever we deal with a not equal sign, okay, this is a two-tailed test. Whenever you have non-equal, that's a two-tailed test. So that means you're going to have two critical values. And you can read those two critical values from this incomplete table. Remember, there should be a plus or minus here. So there should be a plus or minus in front of each of these numbers. So make those corrections in your notes. So for 95%, okay, for alpha of 05, the two critical values are minus 1.96 and 1.96. Okay, so so you have minus 1.96, and this corresponds to alpha equals to 0.05. Okay, and the z critical of alpha over 2. And okay, the other critical value is 1.96. Okay, all right, so those are the two critical values for alpha equals 0.05 for a two-tailed test. Now, where's on this number line, okay, where does negative 1.48675 reside? Well, it resides here. It resides between these two critical values. Okay, so remember, when your test statistic falls in this range with respect to the critical values, it's in the green region. And so in this green region, you fail to reject the null hypothesis. Okay, so we failed to reject the null hypothesis. So what was the null hypothesis? Okay, so go back to the problem. Let's see, did we do that? Did we write that down anywhere? I don't. Oh, okay. So for this particular problem, I think it was. Oh, it was in the notes, right? Okay. So the null hypothesis is that the proportion is 13% per 100 M&Ms. Okay, and so we cannot reject this, even though we pulled eight brown M&Ms out of 100 for our particular sample. We still cannot use that sample to reject this claim that, on average, 95% of the time, you're going to pull 13 brown ones out of 100. Okay, so you cannot reject that. So that's what the data show. And here's the solution. So okay. So that would be a non-technical conclusion for this problem. The sample data do not support the claim that. Okay, no, the sample data support. The sample data show that you cannot reject the claim that 13 out of 100 M&Ms are brown. Okay, you cannot reject that claim. Okay, so that's called the critical value method. Okay, the critical value method. There's another way of solving this problem as well, and that is called what's called the p-value method. Right here, the p-value method. Okay, so since the alternate hypothesis is proportion not equal to 13%, it's a two-tailed test. So the p-value, and now note this is uppercase P, and don't confuse it with proportion. The p-value is twice the area in one tail. Okay, so twice the area in one tail. So we can compute the p-value for this particular statistic. So you compute the p-value from your test statistic. So let me write that down. Okay, that's an important concept. Insert blank page. Okay, so compute not from your critical value, but from your test statistic. Compute the p-value from your test statistic. Okay, so for this particular case, the test statistic was negative 1.48675. Okay, so z-test, all right, z-test equals to negative 1.487, what was it? 48675, 1.48675. Okay, so if we go to our z table, what proportion our probability. What probability relates to this particular z-score, this standard score? So if we go to our z-table, where is it? Here. And we look up negative 48675. So negative 1.41, 0, 1, 2, 3, 4, 5, 6, 7, 8. So 1.48. Roughly 1.49, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0.681. Okay, so the probability for this, so you would say, you would say probability z equals negative 1.49 is equal to, okay, negative 1.49, 0.681. Okay, so your p-value for a two-tailed test, okay, is twice this. So why is it twice this? Okay, which is equal to 0.1362. Okay, so that's your p-value. So you double it because when you go back to the drawing, to the graph, you'll note that the p-value constitutes the area, these two areas. So this is your p-value. Okay, it's a two-tailed test, so it's the area to the left of the critical value plus the area to the right of the critical value in a two-tailed test. Okay, not so in a one-tailed test, but it's the area to the left of the negative critical value plus the area to the right of the positive critical value. So that's the p-value for a two-tailed test, and that's why you double it, because the area to the right of the critical value is what, 0.0681, and the area to the left of the negative critical value is also 0.0681, and then you double those because you have two symmetric areas. All right, so now what do you use this p-value for? Well, okay, so you compare it with alpha. So compare with alpha, so which is equal to 0.05. So you'll note that your p-value is bigger than alpha. Okay, and so if your p-value is bigger than alpha, okay, then you cannot reject the null hypothesis. So let me write that down. If p-value is bigger than alpha, which is your significance level, then you cannot reject H naught, the null hypothesis. Okay, you cannot reject it. If the p-value is low, then the null must go. Is low, then null must go. And that's not the case here. Okay? All right. So that's the second approach to solving this problem, using the p-value method. Okay, so again, and then you state the conclusion in non-technical terms. So the claim is on the null hypothesis equal to in claim, and you failed to reject the null. So there is insufficient evidence to reject the claim that 13% of the M&Ms are brown. Okay, so insufficient evidence to reject the claim. All right, so the p-value method is a method that obtains the value of a sample test statistic that is at least as extreme as the data found in the sample test. The p-value is compared to the significance level, which is alpha, and if it's less than the significance level, we reject the null hypothesis, okay? And if it is greater, we do not reject the null hypothesis. All right, so there's this p-value calculator that you can look up here on the web. I looked at it and it's pretty good. All right, so let's do another example. Test the claim that for adult population of one town, the mean annual salary is given by $30,000. The sample data are this. Okay, so sample size is 17, sample average is 22,298, and the sample standard deviation is 14.2. Use the significance level of 0.05. Okay, so the claim is, an expert claimed that the mean salary is $30,000. Okay, that's the claim. All right, so the counter to the claim is that the mean salary cannot be $30,000. And so the alternate hypothesis is here. Okay, so this is again a two-tailed test because the presence of the not equal sign. So in this case, the test statistic, we're not dealing with proportions, but we're dealing with data that are not, well, let's see, what is NP? So N is 17. Oh, we don't have a proportion. So let's see, which test statistic should we use? Okay, should we use, all right, so it's a mean. The parameter is mean. Okay, should we use T or Z? Well, N, do we know the sample size? What is sample size for this problem? Let me see, look at my notes. Okay, so N is 17, all right? So N is 17, and there was no mention of standard deviation. So and N is bigger than 30, so all right, so it seems to fall into this category, that sigma not known, and there was no mention of the salary distribution being normally distributed. So I believe there was a note in the book that says that if there's no mention of a parameter being normally distributed in a problem, then you can make that assumption. Okay? And so in almost all of these problems, except for proportions, you can assume that the population parameter will be normally distributed, unless it says otherwise. Okay? All right, I believe I saw that reference in the book. Okay, so we have to use the T statistic because we don't know sigma. All right, so the T statistic is here. So what is the question pursuing? It says what? Calculate the test statistic. So in this case, the test statistic will be T is equal to x bar minus mu over S over the square root of n. Okay, so for this problem, x bar was 30,000. No, I'm sorry, the sample mean was 22,298. And the mean salary for the population was 30,000. Okay, and then the sample size was 17. No, the sample size, check that. Sample size was 17, and the sample standard deviation was 14.2. Okay, so what is our test statistic? Okay, so we can go into Excel and find that. Okay, click on a cell, type equals, okay, x bar, okay, 22,298 minus 30,000, divided by square root of sample standard deviation, which was 14,200, divided by the, no, I'm sorry, I shouldn't put the square root there, sorry. I should put an open paren, okay, sorry, I got carried away. Divided by 14,200, divided by the square root of the sample size. Okay, that's better. Okay, and so that makes our test statistic to be negative 2.23635. Okay, so what is our alpha? Now this is a two-tailed test, right? This is a two-tailed test because there's a not equal, and alpha is equal to 0.5. Okay. So alpha equals to 0.05. So our critical value, T critical, okay, you'll have two critical values, right, because it's a two-tailed test, and we can use the T inverse function, right? Now remember, for T inverse function in Excel, you do not have alpha, but if you were doing a table lookup, you would have to have alpha. So that's your probability, and the degrees of freedom are one less than the sample size, so it's 16. And so your critical statistic will be plus or minus 2.120. Okay. Okay. So here's your T distribution. Here is your critical value. And your test statistic is here. Okay, so it's to the left of the critical value. So this is in the region where you reject null hypothesis. Okay, so there is sufficient evidence to reject the null hypothesis and support the alternative hypothesis, which says that the mean salary in the village is not $30,000. Okay, so sufficient evidence to reject the null hypothesis. That's the non-technical conclusion. Reject a null. Claim is on the null, and you reject the null, so there's sufficient evidence to reject the claim that the mean salary is $30,000. Okay, so that was a critical value application of a two-tailed test. So let's talk about the left-tailed test. Okay, so in the left-tailed test, you use the less than sign for the alternate hypothesis. Okay, and you only have one critical value. Whereas in the two-tailed test, you had two critical values. In this case, you have one critical value. And if your test statistic falls to the left of the critical value, then you reject the null hypothesis. If your test statistic falls to the right of the critical value, you fail to reject the null hypothesis. So let's look at an example. Okay, so the principal of a middle school claims that test scores of 7th graders at his school vary less than the test scores of the 7th graders at a neighboring school, which have variation described by sigma equal to 14.7. Okay, so assuming the hypothesis test of the claim has been conducted and the conclusion is to reject the null hypothesis, state the conclusion in non-technical terms. All right, so to answer this kind of question, write out your null and alternate hypotheses. Okay, so the school district says that the standard deviation, or the variation in test scores, is equal to 14.7. Okay, but the principal comes along and says, nonsense. My variation is less than 14.7. Okay, so then to shut the principal up, the school district came along and analyzed this hypothesis, ran a hypothesis test. And what it discovered was that the null hypothesis was to be rejected. Okay, so the symbol for rejected is this, downward pointing lightning bolt, reject. Okay, so what is the conclusion? Okay, so the conclusion is, all right, the conclusion is, let me type it here. For the middle school claim, there was sufficient evidence to support the claim that the principal's claim how do you spell principal? Principal. That the standard deviation of 7th grade test scores of at his school was less than 14.7. So there was sufficient evidence to support the principal's claim that the standard deviation of the test scores at his school was less than 14.7. So that's the non-technical conclusion. Okay, seems straightforward enough. All right, so this problem, I believe, is actually an example of a right-tailed test. So it's kind of out of sequence here. So let's talk about right-tailed tests. Okay, so in the alternate hypothesis of a right-tailed test, you use the greater than symbol, okay? All the alphas in the right tail, and so if your test statistic falls to the right of the critical value, then you reject a null hypothesis. If your test statistic falls to the left of the critical value, you fail to reject a null hypothesis. So let's work this example. An article in a journal reports that 34% of American fathers take no responsibility for childcare. Okay, so this is going to be a proportion problem. A researcher claims that the figure is higher for fathers in the town of Littleton. A random sample of 234 fathers yielded 96 who did not help with childcare. Test the researchers claim at the significance level of 0.05. Okay, find the p-value and state the conclusion about the null hypothesis. Okay, so we're not going to use critical values, but we're going to use p-values. Okay, all right. So here's how we do it. So in this one-tailed test, we do not double the value of the p-value like we did in the two-tailed test. Okay, so that's one thing I'll show you. All right, so what do we have? We have the authority, which is the journal article, says that the population proportion of deadbeats is 34%. Okay, and then some guy comes along and says, well, that's not quite true, it's actually a little bit higher. Okay, so the alternate hypothesis is that the proportion is actually bigger than 0.34. Okay, so what do we have for our statistics? So these are proportions, so our test statistic will be based on proportions, so we can go back to the table. And what do we have here? Okay, we have to use the, okay, so first of all we need to analyze this. What do we have for this problem? Oh, I dropped my notes here. They got tangled up. Let's see. Okay, so for this problem we have a sample size of 234 and a proportion. Okay, so what is our sample proportion? Okay, so p hat. So we had 96 deadbeats out of 234. So what is our sample proportion? So we can go to Excel and find that. So that's equal to 96 out of 234. So 41%. So what is NP? So NP is equal to 96, right? No, 234 times 0.34, right? Which 34% is roughly a third, so a third of 234 is, I don't know, bigger than 70, right? It's bigger than 70 because 3 times 70 is 210. Okay, so NP is bigger than 5, and then NQ is equal to 234 times 66, right? And so that's going to be bigger than 5 as well. So I'll go for the z statistic. Okay, and so the z statistic for a proportion is p hat minus p divided by what? The square root of pq over n. Okay, so that would equal to p hat, which is 96 over 234, minus 0.34 divided by square root of 0.34 times 0.66 divided by n, which is 234. Okay, so that makes our z statistic 2.268. All right, now we need to use the p-value method, right? So in the p-value method, this is a one-tailed test. So it's at alpha equals to 0.05. Now let me check again the nature of the problem. Let's see. Scroll down. Let's take a look one more time. It says find the p-value. Okay, find the p-value. So the p-value will be for this problem will be okay, so it would be alpha was 0.05, right? And so the critical value for 0.05 is what? What is the critical value? Okay, so that makes confidence level of 95. So we need to find 95 in the 95% probability in the table to get our critical value. So in this particular case, the p-value will be, so where is 95 at? 95, let's see, I'm sorry. Confidence level of 95. So that makes a critical value of 1.645, but the p-value is p-value is 0.95, right? No, the p-value comes from your test statistic. So we need to find the probability. I'm sorry, the p-value comes from this. So what is the probability in the standard normal table when this is your z-score? I'm sorry, I had that backwards. Okay, I apologize. So we go to the standard normal table and we look up 2.268. So 2.2, 0, 1, 2, 3, 4, 5, 6. So roughly 0.9881. So the p-value is 0.9881. Okay, so that's your p-value. Okay, now since we're dealing with a right-tailed test, okay, so in a right-tailed test, the p-value, okay, so remember what the p-value is. The p-value is the area to the left or right of the test statistic, okay? So the p-value is the area to the right or left, depending on the test. So if it's a right-tailed test, the p-value is, let me do a better job. Okay, the p-value, in a right tail test. The p-value is the area to the right of the test statistic. Okay. In a left tail test, which we'll just see in just a moment, the p-value is the area to the left of the test statistic. Okay. In a two-tailed test, the p-value is the area between is the sum of the area to the left of the negative of the let's see, okay, I'm sorry, it's the in a left tail in a two-tailed test. Okay. Okay, so in a two-tailed test, okay, we got a couple of things, right? If the test statistic is less than 0, then the p-value is 2 times the area to the left of the test stat. Okay, if the test stat is bigger than 0, then the p-value, okay, is 2 times the area to the right of the test stat. Okay, all right, so 3 things here to know. Know these 3 things. Okay, just checking. Okay, all right, so now, so the p-value for this particular problem, again, was 0.9881. Okay, no, it's not 0.88. That's incorrect. Okay, that is wrong. So let me X that out. Sorry about that. Okay, so it's a right-tailed test. So okay, so we looked up in the okay, so our test statistic is 2.268. Okay, and it's a right-tailed test. And so when we look up the probability for this, remember the probabilities in the standard normal table give you areas to the left of the z-score. Okay, and so the area to the left of the z-score is this number. So the p-value in a right-tailed test, okay, is the area to the right of the test statistic if the test statistic is bigger than 0. Okay, so it's basically this area. It's the area, no, it doesn't actually this doesn't have to be bigger than 0. It could be stuck here. It could be here in a right-tailed test. So basically the p-value is the area to the right of the test statistic. Well, the area to the left of the test statistic is this. So so we actually have to subtract like so to get the p-value. So the p-value is, for this problem, is 1 minus that, which is equal to 0.0119. Okay, so that's your p-value right there. Now, since the p-value is, so what you do is you take this p-value, okay, and then you compare it with alpha. So compare p-value with alpha. So we have this inequality. That's 0.1119, okay? That's less than 0.05. Okay, so in this case our p-value is less than 0.05, and so when your p-value is less than alpha, it's less than or equal to alpha, you reject the null hypothesis. Okay, if p-value greater than alpha, okay, fail to reject. All right. All right, so that's the p-value test. P-value for a right-tailed test. Okay, you calculate the area to the left of the test statistic, then you subtract that area from 1 to get the area to the right of the test statistic, and that's your p-value for a right-tailed test. Okay. All right. So for this particular problem, we failed to reject the null hypothesis. Okay. All right. So what else? What do we have here? Okay, failed to reject the null hypothesis. Okay, and so we found the p-value, and we stated the conclusion. There is insufficient evidence to reject the claim that so in this particular case we failed to reject the claim. So there's insufficient evidence to reject the claim that 34% of the fathers in the town of Littleton are deadbeats. Okay? There's insufficient evidence to reject the claim. So, or in other words of saying, there is sufficient evidence to accept the claim that more than 34% of the deadbeats, more than 34% of fathers are deadbeats in terms of child care, more than 34%. So the alternate hypothesis, there's a significant, the alternate hypothesis favored over the null hypothesis. Okay, so let's go to this question. Let's see here. What's the next one? Okay, this is the psychology problem. So a psychologist claims that more than 5.8% of the population suffers from professional problems due to extreme shyness. Express the null hypothesis and the alternate hypothesis in symbolic form. Okay, use proportion, the true percentage of the population. Okay, so psychologist claims. Okay, so here's a claim that more than 5.8%. So 5.8% is the base. Okay, so for this problem, the null hypothesis is that the proportion of shyness is 5.8%. The alternate hypothesis coming from the psychologist is that the proportion is actually bigger than 5.8%. Okay, so what are we supposed to do here? Okay, so that's the null hypothesis, an alternate hypothesis. So that would be the solution for that particular problem. Okay, that's a right-tailed test, hypothesis test. What's next? Okay, use the given information to find the p-value. Also use 0.05 significance level and state the conclusion about the null hypothesis. Reject or fail to reject. The test statistic in a right-tailed test is that. Okay, so yes, we want to find the p-value for this problem, basically. Okay, so it's a right-tailed test. So you have H naught, and okay, so you have some claim, and then HA is that. So okay, so but we don't know what the particulars are of this problem, but we do know that the test statistic, so Z test, is equal to 0.52. Okay, so now in a right-tailed test, to calculate the p-value in a right-tailed test, okay, so 0.52 is here, right? And so we need to find the p-value will be this area right here. Okay, so we go to our standard normal table and we find the z-score of 0.52. So where is that? If it will open, there it is. Okay, so the z-score is 0. Wait, was that? Z is equal to 0.52. Okay, so 0.52 is 6985, right? So the probability of Z equals 0.52. I should write probability. Is 6985. Okay, so the p-value is the area to the right of the test statistic because of this, of that. Okay, and so p-value is equal to 1 minus 0.6985, which is equal to, let's see, I have it figured out somewhere, 0.3015. 0.3015. And so you compare your p-value with alpha. So compare your p-value with alpha, but alpha was 0.05. So in this particular case, you fail to reject H naught. Remember, when your p-value is bigger than alpha, you fail to reject. But if p is low, then null must go. Okay. All right, so that's that particular question. What else do we have? Okay. So Carter Motor Company claims that a new sedan, the Libra, will average better than 32 mpg. Assuming the hypothesis test of the claim has been conducted and the conclusion is to reject the null hypothesis, state the conclusion in non-technical terms. Okay, so transportation. Okay, so whenever you have a claim, okay, the claim is made against a base. So the base is 32 miles per gallon. So the base is always the null hypothesis. So the mean is equal to 32 mpg. And so the claim is that it's bigger. So this is a right-tailed test. Okay, and so what happened? The hypothesis test was done, and the null was rejected. Okay, so you reject the null hypothesis. Okay. Right, so if you reject this claim, then the data support the substantiation of the alternative hypothesis. So the conclusion is for the new sedan, okay, there was sufficient evidence to support the claim that it gets better than 32 mpg. Okay. All right, so that would be that. Okay, and we've already, okay, so the next problem, we've done that already. Okay, so here's a table that kind of summarizes how to work with p-values, and so I've already done that. I've already written this up. We've already stated that. So let's go and look at some properties of hypothesis testing. Okay, so when you work with hypothesis testing, you encounter what are called type 1 and type 2 errors. Okay, so if you reject a null hypothesis, okay, and the null hypothesis was true, and you rejected the truthfulness of the null hypothesis, then you get what's called a type 1 error. Okay, if the null hypothesis, if you reject a null hypothesis and the null hypothesis was in fact false, then your rejection is validated. Okay, it's always good to reject a false hypothesis. But if you reject a true hypothesis, then it's a type 1 error. Now, if you accept a true hypothesis, then you're okay. But if you accept a null hypothesis that's false, then you have what's called a type 2 error. So let me show you some examples. Suppose the hypothesis is that adding water to toothpaste protects against cavities. Protects against cavities, okay. So the null hypothesis is adding water to toothpaste has no effect on cavities. All right, so if you let's see, what is the type 1 error for this? Okay, so the null hypothesis is false. If the null hypothesis is false, okay, and you reject it, okay, then you're okay. But if you accept this fact that adding water to toothpaste has no effect on cavities, okay, then if you accept this null hypothesis, then you committed a type 1 error. Okay. Now, what is a type 2 error? If you let's see, the type 1 error is if this is false, okay, if this is false and you accept it, then that's a type 2 error. Okay, okay, so if you okay, so this is the alternate hypothesis, right? So if you, what is it? A type 1 error occurs when detecting an effect that is not present. Okay, so, all right, so this effect is not present. So if you accept this, okay, as true, okay, if you accept this as true, then it's a type 1 error. Okay, so let's look at this one. Adding fluoride to toothpaste protects against cavities. All right, so the null hypothesis is adding fluoride to toothpaste has no effect on cavities. All right. So if you accept the null hypothesis, if you accept this null hypothesis, and it's obviously wrong, then it's a type 2 error. Okay, whereas in the first case, if you reject this null hypothesis and it's true, then it's a type 1 error. Okay, but if you accept a null hypothesis that's false, it's type 2. All right, so maybe we can kind of write that down here. So, okay, so type 1. Type 1. Accept. No, you reject a true null hypothesis. Okay, type 2, you accept a false null hypothesis. Okay, so let's look at another example in jurisprudence. This will be interesting for your criminal justice majors. So the evidence produced before court proves that this man is guilty. Okay, so this man is innocent. So if this is false and you accept it, okay, in other words, you let a guilty man free, then that's a type 2 error. Okay, so if this is true and you reject it, then that's a type 1 error. Okay, so you convicted an innocent man. Yeah, so if this is true and you reject it, type 1. If it's false and you accept it, it's type 2. Okay, so let's look at this one. A patient's symptoms improve after treatment A more rapidly. Okay, so the null hypothesis is a patient's symptoms after treatment A are indistinguishable from a placebo. Okay, so if this is true and you reject it, that's a type 1. If it's false and you accept it, it's a type 2. Okay, so a type 2 error means that you're making policy based on, let's see. Okay, so you're making policy based on the fact that the treatment is indistinguishable from a placebo, so you make that assumption, but that assumption is wrong because the treatment is different from a placebo, and so that's a type 2. Okay, all right, so type 1 and type 2 errors, so you can have fun with those. Let's look at an example here. A consumer advocacy group claims that the mean mileage of the Carter Motor Company's new sedan is less than 32 miles per gallon. Identify the type 1 error of the test. Okay, so for this problem, we need to write our null and alternate hypotheses. So the null hypothesis is mean is equal to 32, and then the alternate hypothesis is less. Mean is less than 32, so it's a left-tailed test. Okay, so the type 1 error is what? This is true, but you reject the truthfulness. In other words, you accept this. So the type 1 error would be when you accept this, that the mean is less than 32 when it in fact is 32. Okay, so that's the that would be how you would analyze that. Okay, so let's see here. Is there any other things that I can say about that? Yeah, so you accept the consumer advocacy's claim as true. So you accept that as true when you should not. Okay, so let's move on to the next set of problems. So testing population proportions, as before, we've seen this already. Okay. And so here's a worked example. Based on the information from the National Cybersecurity Alliance, 93% of computer owners believe they have antivirus programs installed on their computers. A random sample of 400 scanned computers found that 380 of them, or 95%, have antivirus software. Uses sample data of the scanned computers to test the claim that 93% of computers have antivirus software. Okay, so yeah, so the claim that 93% have. Okay, so so we're not make. Okay, so in this case, 400 computers. The proportion is 93%. Okay, so NP is 372 and Q is 28, so they meet the requirement for proportion test. N is 400. So we're going to use the p-value method, so it's going to be a doubling up of a p-value once we get the test statistic, right? We need to find the z-test statistic. Before we do that, we formulate our null and alternate hypothesis. Okay, the significance level is alpha, so here's our test statistic calculated out. Okay, so the proportion was 95, right? Where did the 95 come from? 380 over 400. That's the sample proportion. Test statistic is 157. So we look up, we find z equals 1.57. Okay, so for this problem, we go to our standard normal table, look up 1.57, 1, 0, 1, 2, 3, 4, 5, 6, 7. That's 9418. Okay, so that's the area to the left. So we need the area to the right of 1.57. Okay, so that's 0582, and so the p-value is twice, which is 0.1164, and so that's bigger than alpha. So you fail to reject a null hypothesis because it's a two-tailed test. So right here is the setup. So because p-value is greater than alpha, fail to reject a null hypothesis. And the non-technical conclusion is we fail to reject a claim that 93% of computers have antivirus software. There is not significant sample evidence to warrant rejection. Okay. And then they do this using the critical value method, which we did in Chapter 2. So I'll let you guys go ahead and read through the details here. Okay. All right, so the final topic of Module 3 is the chi-squared distribution. Okay, so remember the chi-squared distribution is to analyze inferences about variance or standard deviation. Okay. And it's, again, you'll have 1- and 2-tailed tests for chi-square distribution. So let's do this example. Now, the summary stat right here, this is wrong. Okay, I'll correct it here as I speak. So listed below are the heights for a simple random sample of 10 supermodels. Consider the claim that the supermodels have heights that have much less variation than the heights of women in the general population. So we'll use an alpha of 0.01 to test the claim that supermodels have heights with standard deviation that are less than 2.6 inches. Okay, so this is a left-tailed test we'll be doing. Whenever you see that less than, it's an indicator of a left-tailed test. Left-tailed test. Okay, so for this problem, the null hypothesis is that the standard deviation of the heights of supermodels is the same as the general population, which is 2.6 inches. The alternate hypothesis is, for this based on this particular sample, standard deviation is less than 2.6. Okay, so that's your deal here. So now, since we're working with this, we have to use the chi-squared statistic, okay? And we will not be having alpha. Okay, so chi-squared, all right, so the sample size is 10. Okay, the sample standard deviation, we need to calculate the sample standard deviation based on the data set. Okay, so from this data set, so remember, to get the sample standard deviation, you have to use Excel. Or you should use Excel. You don't have to use Excel, but it's useful to use Excel. So, and I think a couple of you guys had questions on how I did this, so watch how I do this. So I enter the data, 69.25, 68.5, 69, 70, 71, oops, 71, 70, 70, 69.5. Okay, so here are our data, and so we want to calculate the standard deviation. So standard deviation. Okay, and so to select the range, what I do is I select the cell, hold my left mouse button down, select the cell, and then while holding my left mouse button, I'll drag it through the range. Okay, and notice that it populates the cell range in the argument list for standard deviation. Close parentheses, and then I get that value as my sample standard deviation. So here they say S is 0.89. No, it's 0.7994. So that's my sample standard deviation. So I'm going to use that one, not the one the book uses. So S is equal to 0.79974. Okay. And what else do we need? Okay, so chi squared is equal to n minus 1 times s squared divided by sigma squared. Okay, so and sigma, of course, is 22.6. Okay, so we have all the data to calculate our test statistic. All right. And then alpha was, what was alpha? 0.01? Alpha was 0.01. Okay. Okay, so now, this is a left-tailed test. Okay, so you're going to have your critical value here. So we'll call this chi critical. All right, and you're interested in knowing if your test statistic falls to the left here. Okay, so when you calculate your test statistic, is that what they do next? Yeah, so we did this, so we've got this, step 3, step 4 we've done. Okay, so we're on step 6, so our chi-squared test statistic is 0.852. Okay, so the critical value, so where does this critical value come from? Well, okay, so in the table A4 of your text, but in this case we had 10 data elements, so the degrees of freedom is 9, and then the alpha value was 0.01, making the area to the right 0.99. So we need in a left-tailed test for chi-squared. Okay, so not mentioned in the book. I'll mention it here. Let me write this down. This is something you'll need to know. Okay, in a left-tailed test for the chi-squared test, use chi-squared L. Okay, so the chi-squared L value will be this. So you will find, okay, so I'll put a comma 1 here because it's a left-tailed test. You'll use degrees of freedom and 1 minus alpha. Okay, if it's a right-tailed test, okay, if it's a right-tailed test, then you'll do a table lookup of these. Okay, if it's a two-tailed test, okay, then you'll find chi-squared L. You'll have to find two chi-squared values, namely this one, just like you did in Module 2, and this one. Okay, so this is for right tail. Okay, this is for left tail. And the last one is for two-tailed. Okay, all right, so remember these formats, okay? So in this particular question, we need to find chi-squared of 9 and 0.99 in the chi-squared table. So let's look up that in our chi-squared table. So 9 and 0.99, that gives us 2.08789, which is what I believe they have listed here in the illustration. Yeah, right there, 2.088, and so your test statistic is 0.852, so it's to the left of the critical value. So remember, so in a chi-squared test, if you're to the left of a critical value in a left-tailed test, okay, then you reject the null hypothesis and accept the alternative hypothesis that the variation in the model's heights is less than 2.6 inches. Okay, so if this were a right-tailed test and your test statistics were to the right of the critical value, then you would again reject the null hypothesis. If this were a two-tailed test and your test statistic were in either one of those regions, then you would reject the null hypothesis. So the p-value method for the chi-squared test, you can use the chi-squared .dis function. So this 852 is basically your test statistic, degrees of freedom, and you get this, okay, and then you compare it with 0.1. So you plug in your test statistic, okay, this 852 into the chi-squared to get that. You can also use the confidence interval method, in which case you can compute the chi-squared R and chi-squared L, in which case you would have to have alpha. So check out these numbers, 21.666 and 2.088. And you'll notice that 2.6 is outside of the interval, and so if that's the case, then that is in the reject null hypothesis region. Okay, so work through the details of both details, the critical value method. So three things are worked here. Okay, so the first example is the critical value method. Okay, the second example is the p-value method, and then the third example is basically the confidence interval method. So three methods. I need you to understand all three methods, okay? All right, so let's work two more examples for this module. Find the critical value or values of chi-squared based on this. Okay, so in this particular case, it's a right-tailed test, okay, because we're using a greater than sign. N is 9 as alpha is that. Okay, so what is our critical value? Okay, so we use degrees of freedom of 8 and 0.01. We do not have alpha. So let's verify this 20.09, okay? Verify it. So go to the chi-squared table, right-tailed test statistic, not having alpha, degrees of freedom 8, alpha is 0.1, okay? Remember you don't, okay, yeah. Okay, alpha is 0.1, so 20.090. Do you see it? Right here. So there's your choice right there. Okay. What else? So since it's a right-tailed test, you must find chi-squared R. What else about this? Is there anything else here? No. Okay. And then the last problem is it's a left-tailed test. Okay. Sigma less than that. N is 19. Alpha is 0.25. So in this case, you'll have to subtract this alpha from 1 because it's a left-tailed test. So that's 975 and degrees of freedom 18. So it will be, your chi-squared L statistic will be, for this problem, if I'm looking at it right, 8.23074. So that would be the critical value for this. Okay. And of course, if it were a not equal sign here, then you would have to find two critical values, chi-squared R and chi-squared L. Okay, so that is Module 3, and you need to let me know if you have any questions.